All right, so we have some dipole-dipole interactions occurring here between water molecules. And remember we said that the partial negative charge on a water molecule, where is it at?
Oh, it's on the oxygens, we said, because it's more electronegative.
That's right. So the partial negative charge is on the oxygen, or you can see it in the picture here. Partial positive charge on the hydrogen. So that results in an intermolecular interaction. All right. Now this is a molecule that has a dipole, and this is a molecule that has a dipole. And so this is a dipole-dipole interaction. However, there is a special kind of dipole-dipole interaction called hydrogen bonding. And really, I don't know why they call it hydrogen bonding, because the word bond is a sacred word that you should really keep for just intermolecular bonds. Intermolecular bonds are very strong. Hydrogen bonds are extremely weak compared to intermolecular bonds. In terms of, hydrogen bonds are very weak compared to intramolecular bonds, bonds that are in molecules. Compared to intermolecular interactions, though, hydrogen bonding is actually fairly strong. And hydrogen bonding, we call it hydrogen bonding when one of the one that has the partial positive charge is the hydrogen, and the one that has the partial negative charge is one of these three, either nitrogen, oxygen, or fluorine. All right? So when the side that has the partial negative charge is nitrogen, oxygen, or fluorine, and the side that has the partial positive side is hydrogen, then we call this a hydrogen bond. It's a dipole-dipole interaction that's a little bit stronger than your typical dipole-dipole, and we call it hydrogen bonding. Now, notice here are water molecules interacting with neighboring water molecules. All right, so the positively charged hydrogen here interacts with the negatively charged oxygen, with a neighboring positively charged hydrogen, that oxygen with another neighboring positively charged hydrogen, and so forth. And because of this interaction, because of the shape of the water molecule itself, it results in a hexagonal structure. And that's why whenever water in the liquid phase condenses further to a solid phase, ice, right, you get structures, snowflakes you could call them, that are always hexagonal in nature. They always have what's called six-fold symmetry. Or in other words, if I take this and rotate it 1/6 of the way around, it'll look exactly the same. All right, so some of these have threefold symmetry, that's 6 times 2, but all of these different, and there's so many different snowflakes. Snowflakes are really, really cool. I don't know if you ever have a chance to go up somewhere like Idaho where the air is really dry and the snowflakes fall on your jacket and you can just see the snowflakes. It's super cool. But they have that shape, 6-sided symmetry, because of the way that water molecules interact and form hydrogen bonds together. So with this in mind, which compound below is not capable of forming hydrogen bonds? How would you go about doing this one, Fred?
Well, I guess I gotta find out if these molecules are polar or not.
That's right. How would you do that?
I have to draw the Lewis dot structure.
Okay, very good. Water is one of these. We've been looking at that recently. We also looked at ammonia, NH3, kind of significantly. Okay. Would these be able to hydrogen bond?
I can't remember. How do you know?
Well, you draw a neighboring one, right? You draw a neighboring one, and you think about where the partial negative charge is. Here it's oxygen, partial positive, here's positive. And then you see, is that intermolecular interaction between a hydrogen and one of the big three? All right. We know water can hydrogen bond. That was already an example. Can ammonia hydrogen bond?
Well, I guess so, because the nitrogen is one of the big three, right?
That's right. It's one of the big three. So a neighboring molecule of ammonia, partial positive, partial negative, that interaction would be a hydrogen bond. How about HF?
Yeah, we saw that already.
How about CH4?
I'm not sure. What's its shape?
That's a good point. CH4 ends up having a tetrahedral shape like this. So if there was a dipole, which, well, the symmetry right there shows you that there's no dipole, right? So there's not going to be a dipole-dipole interaction. And any intermolecular interaction with a different molecule of CH4, methane, would have to be with the carbon and the hydrogen. And so even if there was, which there's not very much of a slight positive charge on the hydrogen, or slight negative charge on the carbon, even if there was, then you're not going to get a hydrogen bond because carbon is not one of those big three. Does that make sense?
Oh, yeah, that makes sense.
Okay, so which of the following is not likely to have a hydrogen bond? And they ask us to sketch the molecule, right?
I don't know these molecules. How am I going to sketch them?
That's a good question. And we have to learn a little bit more about what kinds of, what's being described when we see this sort of thing. CH3CO2H. What we have to realize is that for a handful of molecules, these are all organic compounds. And so we're learning a little bit about organic compounds. And because, you know, it's just been gradually coming upon us, right? But they usually have a carbon skeleton. So when you see CH3, what that is that's 3 hydrogens on the carbon. CO2 means 2 oxygens. And then 1 hydrogen. Whoops, the hydrogen isn't coming off of there. One of the hydrogens is coming off of there. All right? And now when we see here that we have only 3 bonds to this carbon, this oxygen here has to be a double bond. Okay? So that's our first one. Our other one, C, 3 hydrogens. And then an O with a hydrogen coming off it. C, 3 hydrogens, 2 oxygens, another carbon with 3 hydrogens. All right? So we won't have it so that you have to know how to draw these, but it is something that you need to gradually kind of be more and more familiar with. Okay? So, what do you think? Which one is not likely to have hydrogen bonding?
Am I looking for, like, hydrogens? I don't know. How do I know?
Well, what we need to look for is dipoles. Dipoles.
What's a dipole?
Well, you know, like where the partial positive and partial negative charge would be, like a polar part of the compound. So here, this carbon-oxygen bond, you'd have a partial negative here. You'd have a partial negative here and a partial positive here. Partial positive here as well. All right? Because those oxygens are polar. Right? Or those oxygens are electronegative, which result in polar bonds. Partial negative here, partial positive here. Partial negative here, partial positive on the carbon. Same thing over here. Now look at that. That's kind of symmetric, isn't it? It has a degree of symmetry. I haven't drawn it exactly right because the angle between, there's 2 lone pairs there that I didn't include, right? The angle between this bond and this bond here would be 4 regions of electron density, a little less than 109.5. So it's not completely symmetric, but there is a degree of symmetry which would weaken the dipole moment there. All right? And also, in this compound here, a neighboring compound that looks like it does not have any hydrogens coming off of oxygens. And so this hydrogen here isn't going to really bond much to this oxygen because this is not a strong dipole, that carbon-hydrogen there. All right? So for this here, I think we've found that this intermolecular interaction is not going to be a hydrogen bond interaction. I could draw hydrogen and oxygen of a different CH3OH here, right? See that? And this dipole is interacting with that dipole, and that is a hydrogen bonding dipole-dipole, right? Because the oxygen has the hydrogen there. Same thing here. There's that OH group. But because this one over here doesn't have an OH group, then that one's not going to be able to hydrogen bond. Does that make sense?
I think I understood that.
All right, good. So, which statements are true of molecules that exhibit dipole-dipole interactions? Is the molecule polar?
Yeah, you got to have polarity.
That's right. Is it asymmetrical?
Yeah, you got to have asymmetry.
Does it have to contain hydrogen attached to fluorine, oxygen, and nitrogen?
Yeah, well, let's see. What is the question asking? Which statement are true? So are you asking which ones can hydrogen bond, what you need to hydrogen bond?
No, it's not asking that, is it? It's just what does a molecule need for there to exist dipole-dipole attractions between them?
Yeah, so it would just be 1 and 2.
Why not 3?
Well, that's what you need if it was a hydrogen bonding.
That's right. Very good. Good job. Now let's talk about, well, this is a good place to stop. We'll talk about London dispersive forces next class, or next lecture video.